Hi guys, my name is Marcin. I'm data engineer and consultant at Tantus Data. Previously I've been working for companies like Spotify, Truecaller, and most recently Apple. The title of this talk is Apache Spark, if only it worked. And it might sound a little bit provocative, but let me explain. So quite some time ago, when I was working with my first Spark application, I was looking for a solution for my problems, and I found this blog post, explainmydata.com, and the title of the post was Spark should be better than MapReduce if only it worked. So the author of this post was giving some advices about Spark and how to make it better, but he was also complaining quite a lot about how hard it is to make Spark reliably and how hard it is to make basically work. And honestly, at that time, I felt exactly the same. But fortunately, quite a lot has changed since then. So I've learned quite a lot, and Spark has significantly improved. So during this talk, I'm not going to put you off from Spark. I'm going to share my lesson learned, so it will be easier for you. So during this talk, I'll start with execution model. So that will be our foundation to understand Spark and reason about various problems. And then we'll go through a bunch of very common problems you can face while you're running Spark. So we'll have a look at how to size executors. We'll have a look at what Skew Data is and how to sort it out. We'll have a look at locality. I'll introduce you to Spark caching. There will be a few words about debugging tools and running Spark locally and testing Spark. And at the end, there will be kind of a competition or a draw. So yes, stay tuned. So as you can see, there is a lot of information squeezed in. So those of you who are working with Spark should get some hints. And those of you who are not, who are planning to work with Spark, they'll get an overview of what to expect. How many of you are working with Spark? Not that many. So Spark is general engine for distributed data processing. It provides an API for various languages. It has streaming module, it has machine learning library and SQL support and so on. But for today's talk, we're just gonna focus on the core distributed data processing engine. So let's start with execution model first. Spark introduces an RDD. It stands for Resilient Distributed Dataset. And basically, it's an API which lets you feel that you're working with local collection, but the actual data is distributed into partition and spread across the cluster. So what Spark does when it's running the program, it actually pipelines operations until they can be done on one partition, until they can be done in separation. And it is quite nice optimization because it lets Spark to do bunch of operations in memory, but eventually you need to exchange data between partitions. So such a group of pipelined operations is called stage. And then when you want to exchange the data, so for instance, when you want to do a group by key, you want to pull all the same keys into one place. And such an operation is called shuffle, and this is what you usually want to watch out for because it involves disk, it involves network, so a lot of I/O. It's expensive, basically. And your application most likely consists of multiple stages and multiple shuffles. So far, I was just saying Spark does this and that, but the actual execution unit in Spark is task. And task consists of two things: the instruction of what to do with data, so your code, and the data itself. So, for instance, a block in HDFS. And if you have a look at the picture I showed you before, each stage consists of multiple independent tasks. Each task gets run in JVM called Executor. You control how large the executor will be, so you control how many CPU you want to give to it and how much heap memory. And depending on how many CPU you give to it, there will be as many tasks run at a time in the executor. And the at a time part is very important because when executor is done with running a task, it just picks up another one. So basically, executor is long-living JVM, and it has certain consequences. Each executor is orchestrated by single driver process. So we know about tasks, we know about executors, and you want to submit your code. So the question is how large you want your executors to be. And you have various options. You can start from like very small executors with one CPU and a little bit of memory. On the other edge is the very large one, which is taking most of the node resources. And you can choose virtually anything in between. The actual answer really depends on your workload, but I'll give you some things to keep in mind and some hints about it. So let's start from the very small ones. The very small ones are, I would say, just fine, but in some cases they might be not optimal because Spark can benefit from running multiple tasks in the same JVM. So for instance, there are broadcast variables which are copied to every single JVM, and if you have a lot of small ones, you end up with a lot of copies of the same data. But in general, small ones are kind of safe. The very large ones, on the other hand, I've experienced a lot of problems with them because very large ones means a very large heap space, and I've observed a lot of garbage collection problems with them. So I would say, if you are not sure, I would start with 1 up to 4 CPUs and then see if you want to do something more complex, something more advanced. Before we go a bit further with sizing executors, I want to introduce you to Spark memory model. I mentioned the heap memory. You control that. But the heap memory is split into 3 areas. One is for caching, the other one is for intermediate buffers used during shuffle, and the last one is for user program. And up until Spark 1.5, you could control them explicitly. So for instance, if you knew that you are not caching anything, you could set the caching area to 0 and save some heap space. From 1.6, Spark tries to balance it automatically. But if you feel that you know what you're doing, you can still control them. You can still use the legacy options. And there is one more area which is outside of heap. This is memory overhead, and this is used, for instance, for Yarn. If you're running Spark in Yarn containers. This is used for container-related overhead, but also if you are using libraries which are writing off-heap, data, that's where the off-heap data goes. So you should keep the memory overhead in mind, especially if you use off-heap data, but also you should keep that in mind if you're doing your calculation of, let's say, how many executors you can fit in your node. It's not enough just to take the heap memory into account. You have to take into account both. Some other hints are keep some resources for your operating system. If you are using Yarn, hopefully your admin took care of that. But if not, make sure you are not too greedy because it's just not gonna work. If you are not sure about what's going on, how much memory you are using, you can always play with Spark, cache an RDD, and then Spark UI will tell you how much memory the RDD is taking. If you have a job which if you have a single job which sometimes is taking very large input and sometimes very small, you can also play with something called dynamic resource allocation. And the idea is quite simple. So it starts with small number of executors, and it increases it while the job progresses. So and then it can kill executors which are idle. So now I want to kind of assume that we have our code. We are ready to submit it to the cluster, and mention a few. And I want to mention a few problems which you will probably face if you're running Spark for the first time. But before we do that, we really need to zoom in a little bit into Shuffle, because that's the root of most of Spark problems. So this is what Shuffle looks like. When a task is about to finish, it prepares data for Shuffle. So it splits data into buckets. So each bucket is responsible for certain keys. Those buckets get stored into local disk. So they are ready to be picked up by another stage, by task in another stage. And then all the red buckets from local disk can go to the same place, and so on. So this is what it looks like in theory, in the perfect scenario. But this is what it might look like in practice. So task 1 is a little bit heavier, and then the keys are not really evenly spread, and everything explodes. And one of the reasons for the explosion, for the failure, is that Spark has a limitation of 2 gigabytes for buffers which are used during Shuffle. And the reason for that limitation is basically implementation detail, but this is something we should be aware of, and we should handle somehow. So it's very likely that when you're running Spark for the first time, you can see either the 2 gig problem, or some timeouts, or some heap-related problems, or maybe this cryptic executor lost failure message, which doesn't tell you much, at least at first glance. So one of the So I'll actually show you now what to watch out for in the Spark UI. So Spark UI is quite nice. It tells you, it shows you quite a lot of various information, but one of the very important one is your execution plan. This is what it looks like. But some others are task-specific information. So for each task, you get some stats. So what you definitely want to pay attention for is a tasks which are failing. You want to pay attention to overall duration of your tasks and garbage collection time. So you want this time to be not too large. You want them. It would be perfect if those times are spread evenly. And yeah, those are, if they are too large, they are indicator of something wrong going on with your job. The other very important thing to keep an eye on is Shuffle-related stats. So how much data is being produced or consumed during Shuffle. And again, you want it to be not too large and perfect. It would be perfect to have it evenly spread. But if you run Spark, is very often that you see one of these problems, and the very first thing to check is if your tasks are not processing too much data. And if you suspect that your tasks are processing too much data, the easy solution would be to increase the level of parallelism. So you create more tasks. So each task at least you expect that it will be processing less data, and that should be the easy solution. And you control level of parallelism by passing number of partitions parameter to any method which is triggering shuffle, like group by key, or you can trigger a kind of artificial shuffle by calling repartition. So that artificial shuffle will be somewhere in the middle of your stage. The other easy solution would be to increase your memory. It might help, but of course that doesn't, you cannot do it forever and it doesn't scale. But sometimes just increasing level of parallelism is not enough. Sometimes you deal with skew data problems, and that means some of your keys are just much more common than the other ones. So even though you have a lot of tasks, most of them are doing nothing. There is one task which is processing half of your cluster data, and it just cannot keep up. So the very generic way to solve skew data problem is by adding salt to your keys. So basically, you want to add some junk to your keys. So in this case, we have foo, which is often. And we split that into 2 buckets. So these buckets can be processed in separation. And then you probably want to merge the results. So the details might depend on what exactly you are doing, but this technique is you can use very often, and it's really powerful. Other thing you could check, and you probably want to check if you're not happy about your Spark job performance, is locality. So the concept of locality is very simple. Basically, you want to run a task reading data on the same machine the data is. So if you're running HDFS blog from node 1, you want the task to be run there. So this concept has been borrowed from Hadoop. If you want to check locality, you again go to your Spark UI, and if you see a lot of locality which is lower than node local, you might want to try to improve that. And you improve that by basically using more executors, increasing number of executors. And when you increase number of executors, there will be basically much higher chance that there is an executor which is free and ready to pick up a task in expected locality level. You could also play with Spark locality wait parameter, and it's a hint to Spark for how long it should wait for an opportunity to run a job with expected locality level, and after that time it just gives up. So this parameter can be used for enforcing locality or giving up locality entirely, but in most cases the 3 seconds value, the default value, is good enough. And for small jobs which are not reading that much data, probably you don't want to pay too much attention to locality. I mentioned RDD so far, but I haven't told you very important thing about RDD yet. So RDD gets lazily evaluated. So what that means is that if you instruct Spark to read some data and then you apply an operation like filter or map or flat map, nothing will really happen on the cluster. Something will happen on the cluster only if you call an action. So example of action is saving to disk. Then it will calculate everything at a time. But there is a caveat here. If you're reusing an RDD, the calculation of the RDD will happen twice or multiple times, depending on how many times you're using it. And that might worry you, but it's not really that bad, depending on the situation. So in some situation, you just can live with the fact something will be calculated twice. But if you are not happy about it, you can use Spark caching. So Spark lets you cache your data in memory. Spark lets you cache your RDD in memory. And every time you can see a branch in your execution plan, every time you reuse an RDD, you should basically ask yourself if you want to cache that data or you don't care that much. If you are not sure about memory consumption, you can check how much RDDs, cached RDDs are taking in memory, and it's very important to know it, because if you have a few RDDs and all of them you want to cache, you have no way to pin an RDD to memory. You have no way to set a priority on an RDD. So it might be that by caching an RDD which is not that expensive to calculate, you lose and you evict an RDD which is already in memory and it was very expensive to calculate. So it's very important to know what you're caching and how much memory it's taking. If you are running out of memory but you still want to save your computation result, you can cache to disk. You can cache to disk with replication factor. You can cache. You can do checkpointing, which is basically caching to HDFS. But those operations are very expensive, and I would recommend to be careful with them. Last comment about caching is that when you're planning your caching strategy, it's worth remembering that the shuffle data, the colorful buckets, get stored on local disks, so they can be reused later. So the recomputation doesn't necessarily start from scratch. It will start from the last shuffle. Quick zoom in into join. It's basically the join is based on what's going on with shuffle. So you pull all the red buckets from two stages into one place and you join them together. I'm showing you this picture only because it's very similar to the group by shuffle I showed you before, and that similarity can be used by Spark. So basically, if you are nice to Spark and if you do certain operations, certain hints, it will actually optimize your job. So in this query plan, we have two group bys. We apply a map function to each of them, and we join the result together. But if we are using the same number of partitions for each group by, and if we tell Spark that we are not modifying keys, and we do that by calling map values instead of map, Spark can change this execution plan into that one. So both group bys are happening in the same task. The map values is executed in memory, and the join is executed in memory as well. So we had 5 stages and 4 shuffles. Now we have only 2 shuffles. So avoiding 2 shuffles is usually very, very big improvement. So basically, be nice to Spark, and it will be nice to you. Another way to improve your shuffles, and when I say improve shuffle means avoid shuffle usually, is using broadcast variable. So this is type of variable which gets copied to every single executor. So imagine you are joining 2 RDDs. RDD1 is a very large one. RDD2 is tiny. So instead of doing shuffle join, you can broadcast the RDD2, so it's in memory of every single executor, and then you can join to each partition of RDD1 in memory. So you don't need shuffle at all. You don't need to shuffle the large RDD1. So just some recap of optimizing shuffles. Control number of partitions. Use map values if you are not modifying keys. Use broadcast variables. Filter before the shuffle, not after the shuffle. That's quite obvious. Avoid group by key. So far I was showing you group by key quite a few times. But I was doing that only because I assumed most of you are familiar with the concept. Reduce by key is much better. It does an optimization in terms of what's getting sent during shuffle. So the optimization is kind of similar to what Combiner in MapReduce does. Few words about debugging tools. Spark UI is your main debugging tool, and you can get a lot of information from there. You just have to know what to look for. It's worth looking at your HDFS monitoring tools. So if you have Ganglia or any system like that, it will tell you what's going on with your cluster, with your CPUs, with your operating systems while you're running your heavy job. Make sure you aggregate your logs. So if you are running on Yarn, you can just turn log aggregation on, and all the logs from all the containers, from all the clusters will end up in the same location in HDFS, and it's very convenient. Make sure you enable logging by default things you find commonly useful. So for me, it's just, there is no question. I want to have garbage collection logs enabled by default, and it's very handy. You can also run Spark. You can also run Spark locally, and it's super handy when you dealing with certain problems like memory, like garbage collection problem. You want to know what's going on your heap and so on. It's just easier to reproduce it locally. And since you can run Spark locally, you can also test it locally very easily, and you should just do it. I wanted to show you a demo, but I don't really have a time for that. But instead, I created a challenge. So that might be your very first Spark application. The use case for the challenge is that we want to read CSV file, and we want to output certain fields of the CSV file together with randomly generated UUIDs. And on this link, you have the solution for that problem, and it works. The only problem is that you observed that when you're increasing a number of CPUs per executor, you actually don't see any performance improvement. So the challenge is to fix that. You get full description on the link. So some summary. I cannot stress more that you should test your Spark application. And it's not only about quality, it's also about how fast you can iterate. So if you're testing your code, you're basically iterating much faster. You don't wait for resources. You don't really wait for the job until the job finishes on the cluster, and just to see that you have some silly bug. You just do it locally, test it locally, and you iterate much faster. You are probably not the only user of the cluster, so make sure your optimizations are not really affecting the other users too much, so you are not too greedy when it gets to how much memory you get, and so on. And make sure you know what you're optimizing for. So if you're optimizing for resource consumption, or if you're optimizing for wall clock time, this is not Olympic Games. Just be pragmatic about it. You're probably working in a team, and there are developers, there are analytics, there are some people who want to run a SQL command from time to time. Make sure you've come up with some best practices and share them across the team. Make sure also that you review what's going on your cluster to spot bottlenecks. And the last comment is somehow related to the title of this talk. So Spark actually works. You just have to know what you are doing. You just have to understand what's going on under the hood. But the more you know, the nicer it is to work with Spark. So yeah, we have some time for questions, if there are any.
How Spark partitions a data frame when the input is a Hive query?
Can you repeat?
How does Spark partitions a data frame when the input is a Hive query?
So when the input is Hive query, you most likely are reading from HDFS. So it's basically HDFS partitioning. Oh, sorry. So the question was how Spark does partitioning when it's reading the data, when it's running a Hive query. So when you're running a Hive query, when you're reading data from HDFS, Spark does the default HDFS partitioning. So data in HDFS is stored into blocks, like 128 on megs or something like that. So Spark reads the data block by block. So each block means a task. So there will be a task created for each block in HDFS.
But if the query has some aggregation functions using distribute by clause, does it help to Spark about distribution strategy?
Say it again.
So if the query says, let's say query contains some aggregation functions like sum, average, or if I use distribute by clause in the HQL, does it help Spark about partitioning data? See what I mean?
No, not really. We can take it offline. Yeah. Anyone else? All right, thank you.